Welcome back. Mathematics 2, the first exercise sheet, 7.1. This is the numbering from our lecture course, so that's why I jumped to 7 now. This is about power series, better speaking, infinite power series, which are constructed in a way that you sum up, just look at this example, you sum up by concept an infinity of terms of this kind. Now, this factor here, which is a constant, not really, but it's at least it's not dependent on the variable x. This is called the coefficient generally. Let's look here. This is more general. So this is summing up from usually counting starting from 0, then up to infinity. So this is the coefficient of this series, ak, and this is why we have been talking about infinite number series before, because and also asking the convergence question. Okay, is such a series summing up a certain infinite sequence, is it convergent? Is there a limit value or is it not? Okay, is it divergent? But now, newly, we introduce a variable x again. So this has very much to do with differential calculus, of course, yeah. And we may subtract another constant here, which is called x0, or sometimes also a. This is my notation now. This is, you could say, the position at which we construct this power series. So the nearer the variable x is to this, you could say, starting value x0, the better the convergence will be in general. And then, but you see the well, roughly speaking, these are all powers of x with a rising exponent. And so it's nothing else than constructing a polynomial which theoretically reaches an arbitrarily high degree. And now, in practice, these power series are mostly used to approximate certain, often analytically given functions, which are otherwise hard to calculate. Even using a pocket calculator or any algebraic software gives you just the illusion of a machine that is able to calculate something like Euler's number e to the power of square root of 7, for example, okay? So in reality, the machine reduces an analytical expression to such a power series, and then in practice, this process is disrupted at a certain stage, so that you of course, you can't calculate the sum of an infinity of elements or terms. Instead, you will decide to say, okay, I try and use the first 5 or first 11 of these terms and find out how well it works, like how high is the precision that I achieved with this number of steps. So that, you know, that's the practical reason for being concerned about power series, and the reason why we do these exercises. Now, let's look at the first one. It's about power series and convergence radius. We also say radius of convergence. Well, the expression radius might be a little confusing because you are thinking of a circle. Well, that's mainly due to the fact that power series are often, or more in general, looked at in the domain of complex numbers. While in this exercise sheet, all these power series are in the real domain, in the one-dimensional number domain, right? So, but still, we use this expression. You can also call it convergence interval, but then you must take care. If I say radius, look here, I mean, I don't mean really the length of this convergence interval. Instead, I mean half of it, like in the sense of a one-dimensional circle. So that's clear, okay? I guess it's not the diameter, it's just the radius of this interval, right? So, but there are many theorems about it. One of them says that you have a symmetry here, so that if this is our starting point, x0, you have convergence area which reaches to the right and to the left for the same distance. And now there are several possible ways to calculate this convergence radius. So first of all, what you see here is that the coefficient sequence is obviously the well-known harmonic sequence of, these are reciprocals of natural numbers. And we all know, if we just ignore, let's just suppose this x term were gone. We all remember that the harmonic series, given in this way, is divergent. So it does not have any limit value. It doesn't approach anything, it approaches infinity, okay? So that would be a problem, because it would suddenly mean that our power series does not converge. But now that's the interesting point. Depending on which value of x you choose here, and also the nearer it is to the 1, the smaller this contribution gets, a number between 0 and 1, for example. And so this effect may lead to a convergence of the whole expression. And that's true. That's what happens. Now, to get a little more familiar with this, that this is a very compact notation. Let's just look at the first few elements or terms inside this summation notation. So the summation sign is familiar to you. And of course, it means that starting with n equals 1, we just insert here. So the first element will be simply 1 by 1, 1 over 1, which is 1, and then x minus 1 power 1. So that's it. That's a linear term first. There might be a 0 element, but not if using this harmonic sequence, then it's impossible to divide by 0. But as I told you, in general, you have a 0 term also. Now, this is the first term. The second is plus, you see, 1 over 2 then, and x minus 1 in parentheses squared. And then you get your cubic term, etc. Interestingly, in most cases, so this, you could say this is, if this represents a certain function, which we don't really know and won't even find out in this example, you can say this is the best possible linear approximation to that function. And taking this additionally, these two together then form the best possible quadratic approximation to that function. So that's quite a nice idea behind it. Okay. Now, don't be confused by this -1, which is subtracted. This just means that this is, you could say, our development position where we or expansion point, you could say, where we construct this series is often chosen to be 0, but this time it's chosen to be 1. Okay, so we look at the behavior of that function in the neighborhood of x equals 1. That's the best way to say it, I think. So now I write the following: the convergence radius, or the radius of convergence, equals, if it exists, it equals the limit of this expression for k approaching infinity. And this should be quite familiar to you. You should, probably you remember this sort of expression, but please don't mix it up. It's true. It goes back to the so-called ratio test, which you remember as a convergence test for, for infinite number series. But this time, the ratio is reversed. So this time, an element of this coefficient series or coefficient sequence is in the numerator, while its follower, its successor element, is in the denominator. When you used, or if you remember the ratio test for convergence, you will know that in the ratio test, it's quite the opposite. It's the other way around, right? But that's, there is a theorem, I think Martin even proved it in the lecture, which, you can say, which connects this situation with the ratio test, and so actually it's derived from the ratio test, okay? But then in the end, it's this way around, not the other way around, right? So you just remember that. And also it's always about absolute convergence. So these signs for absolute value have the usual purposes. Their purpose is to remove any negative signs which might appear, so that a possible supportive convergence effect of a sign change will not be considered here. So let's go on. I just put AK here. So following this scheme, I just take this 1 over n from here, but now this time using k as a numbering index. So it's called 1 over k. And then the whole thing over the quantity 1 over now k plus 1, because this is the next element, right? In the sense of a index k plus 1. Now, what is this again? This is a double fraction. We can simplify it, so we get, and then I can remove also these absolute value signs, of course, because everything's positive here. So we get the limit k approaching infinity of the quantity k plus 1 over k. And now this is quite nice. You could even split it, okay, because this fraction is the same as k over k plus 1 over k. In other words, 1 plus 1 over k, and then the part behind approaches 0. So but you all know that with a fraction where the degree of the numerator and the denominator terms are equal, it always has a limit, which is the quotient or the ratio of the leading coefficients, okay, factor 1, factor 1. So anyway, the limit is 1. And that means that this series is convergence, at least inside the interval. You see, if 1 is the convergence radius in the sense of this here, so it's the interval from 0 to 2. But now, an important feature of this theorem here that we use is the fact that it can only tell us something about the open interval. So it guarantees us that the series is convergent, let's say, preliminarily for 0 lower than x lower than 2. So this is the open interval, right? But at this place in blue color, I already state that it's even convergent for 0, for x equal to 0, but not for x equal to 2. So usually, if you are interested in this question, you should, well, there might be several possibilities, but the best possibility is just insert these limit values, or these these limiting values of the interval, just insert them by hand into your series. So for testing, right? So let's do this. At x equals 0, I just choose x equals 0 and insert this into this expression. So I get, and by the way, this is my way of notation. You don't need to follow it. This P stands for power series, right? And the 1 as an index refers to this, as I called it, expansion position here for starting point 1, whatever, yeah? So that's just my way of notation. Now, P1 of 0, what is it? It's looking here. Inserting x equals 0, then I get -1 as a first term, as a first value, plus 1/2, and always in these parentheses I have a -1. So then -1 squared, and the next one is plus 1/3, and then -1 to the power of 3, and so on. Now the nice thing about this is, as you know, that this factor of -1, which appears here for the first time, and then here, disappears every second time, because if I have an even exponent, it gets neutrally a factor of 1. But then in the next step, with an odd exponent, it gets -1 again. What does it mean? In the end, it means that what appears now is sort of an alternating harmonic series. And then at this point, you should remember well, at least the Leibniz test, okay, which states the following. Or let's first of all, let's do the following. Let's just pull this minus sign outside of the whole expression. I will tell you why. Because if I do this, if I take this minus sign outside, then this changes to minus, this changes to plus, this changes to minus, and so on. Okay, so then it's still valid. But now inside the parentheses, this is the usual appearance of the so-called alternating harmonic series. Why is it? Because the first element regularly has a positive sign. So, and this is a series which is well known and which has been examined very, very accurately, and then it turned out, firstly, by applying Leibniz, the Leibniz test, which states that an alternating series with a zero sequence inside, you know that the harmonic sequence is a zero sequence, it approaches zero itself. And then by the alternating sign, the summing up means that you are guaranteed to find a limit value. Better speaking, this I should say differently. It needs to be not only a zero sequence inside, just ignoring the sign for a moment, yeah, but also a monotonically decreasing series. So you could say a monotonically decreasing zero sequence summed up with alternating signs is convergent. And now, interestingly, this is by using a so-called Taylor series, which will be a topic in the next session. You will find that this expression here, this alternating harmonic series, converges against the natural logarithm of 2. That's quite a fascinating result. And since we extracted a minus sign here, our limit here at this place is negative ln of 2. Now, this was not part of the exercise, but I just told you for interest. On the other hand, choosing x equals 2, look back here again. Now, this time, we have the situation that here, look here, that 2 minus 1 is 1, positive 1. Also here, also here. So we just have factors of 1 squared, 1 power 3, and so on. So there doesn't appear any negative sign anymore. What we then get is the simple original harmonic series. And this is what we have long known to be divergent. Okay, so this is obviously and quite securely divergent, and that's why our power series altogether is not convergent at this right limit of the interval. Now, in the end, it would be interesting to find out which analytical function this series represents, which is possible to find out, but which is not part of this exercise. Okay.